Welcome back to online lecture 7 on unit number 2, thermal design of refrigeration system components. Uh, Today's lecture we will discuss numerical on condensers, mainly air-cooled condensers and water-cooled condenser. As far as air-cooled condensers are concerned, there is one uh, common general configuration of air-cooled condenser, that is fin tube air-cooled condenser, means plate type fins and tube type. This is a air-cooled condenser. And as far as water-cooled condenser is concerned, we mainly focus on a shell and tube water-cooled condenser. And as far as shell and tube condenser is concerned, well, we have already discussed in previous lecture that shell and tube condenser, there is only one preferred configuration, that is refrigerant through shell and water through tubes. That is the configuration. So like evaporator designing, on the similar line, we can design condensers also, especially shell and tube and condensers. Only in air-cooled condenser, unlike evaporative condensers, air-cooled condenser design is not that much difficult. Uh, Shell and tube condenser and shell and tube evaporators are same. So the equations used for the analysis of condensers are mainly, this is the basic equation if we have to design a new condenser. So that is in terms of area, and all four temperatures are given, design temperatures are given. This second equation, that is in terms of enthalpy. Sometimes if the enthalpy values are given or some pressure ranges is given, then we can also calculate QH by using enthalpy difference and mass flow rate of refrigerant. Uh, then if the water cooled condenser is there, the here amount of heat absorbed by water, that equation also we can use for calculating the rate of heat transfer in the condenser. And for if the air cooled condenser is there, the same equation is used. Only in that case, the MCP delta T of air. So TO is the outlet temperature of the air, Ti is the inlet temperature of the air. Again, for air cooled condenser, the condensing capacity is also obtained by using this expression. So that is cooling capacity, heat rejection factor, then TD correction factor, that is temperature difference correction factor, and altitude correction factor. Because air-cooled condenser is mainly influenced by ambient, so the TD correction factor and altitude correction factors are common. TD correction factor, because most of the air-cooled design are the factory assembled units, so they are readily available in the market. So while purchasing, generally most of the air-cooled condensers are designed for 30 degree Fahrenheit TD, or in Celsius it is 16.66 degrees Celsius. So that is in Celsius. Heat rejection factor is again depends on the type of compressors to be used. Generally, the heat rejection factor for hermetical seal compressor is high, and heat rejection factor for open type compressor is comparatively low. So for typical open type compressor, the heat rejection factor is 1.05 to 1.1 or 1.2 maximum. That is if the uh, air cooled condenser is there. So in that or air cooled compressor is there, heat rejection factor. So if the, because it depends upon the heat rejection factor is nothing but the ratio of heat rejection divided by cooling capacity. So generally this ratio is greater than 1. So for example, if the heat rejection factor is 1.2, means condenser rejects 20% more heat than the evaporator absorbs the heat. Means suppose evaporator, if it absorbs heat 100 kilowatt, then condenser in that case dissipate heat 120 kilowatt. Because 20 kilowatt heat is added in the compressor during compression stroke, and also due to absorption of heat from the motor. That's why the heat rejection factor for hermetically sealed compressor is more. So generally it lies between 1.2 to 1.4 depending upon the capacity of the system. But for open type compressor, that heat rejection factor is 1.05 to 1.1. So heat rejection factor, again, it depends on the compressor to be used, type of compressor to be used. TD correction factor that we already discussed, that is if it is designed, if your temperature difference is 30 degree Fahrenheit, TD correction factor is 1. If it deviates from 30 degree Fahrenheit or 16.6 degrees Celsius, in that case, there is correction need to be incorporated. So that correction is generally given in numerical also, or in the table also it is given. Altitude correction factor, it mainly requires because at the ground level, if it is used, condenser is used, then the altitude correction factor is generally considered as 1. And if it is used above the normal sea level, then the correction factor decreases. So as the elevation from the sea level increases, the correction factor decreases. So this is about the condensing capacity obtained for air-cooled condenser. For water-cooled condenser, sometimes heat rejection factor is given. So with the cooling capacity and heat rejection factor, also we can calculate the condensing capacity, that is UH naught. So these are the equations available for condenser designing. In addition to that, the remaining equation of heat transfer remains same. Now we'll straight away go to the numerical part. So this is a numerical. First, we'll take numerical on air-cooled condenser. So an air-cooled condenser for a package air conditioning unit is to be designed to transfer 22.2 kilowatt of heat. So the condenser capacity is given, that is 22.2 kilowatt of heat from R22 condensing. For R22, condensing inside 1.27 OD, outer diameter is given, and 1.12 centimeter ID at 55 degrees Celsius. So 55 degrees Celsius is condensing temperature, and the condenser is to be designed to transfer the heat 22.2 kilowatt. The mass flow rate of refrigerant is given 0.162 kg per second. The refrigerant side heat transfer coefficient is given. The air circulated over the coil. So these are the air cooling coils, or um, air cooled condensers. So the cooling medium is used as air. So air circulation rate is given 120 cmm. Entering at 40 degrees Celsius, so air entering temperature is given. Air side heat transfer coefficient is given, that is 16.4. Now you can here the question is there, why fins are provided at the outer side? Because outer side heat transfer coefficient is very less, inner side heat transfer coefficient is very high. So if you provide fins at the inner side, it's of no use, because the overall heat transfer coefficient is always under the influence of lower of the two film coefficients. So lower of the two film coefficient is 16.4. So this is air side. So air side heat transfer coefficient is very low. That's why air-cooled condensers are less effective than water-cooled condenser. And this is here refrigerant side heat transfer coefficient. The phase velocity of the air may be taken as 6 meter per second. Velocity is given. The air side has 6 fins per centimeter, so that the fin surface to outside bore tube surface area is 20. So 80 by a that bare surface AO is given, that is 20. Determine the fin surface area of the condenser. So condenser fin surface area we have to determine, and neglect resistance of the metal wall and assuming efficiency of the surface, that is 0.9. So this is air-cooled condensers. So first of all, we have to decide which approach to be used. Similar to our evaporator, first of all, we have to decide the approach. And again, if you see both temperatures are the inlet temperature is given. So 55 degrees Celsius condensing temperature is given, and 40 degrees Celsius is what mass flow rate of evaporator. Sorry, mass flow rate of air is also given. So we can calculate exit temperature by using MCP delta T, because mass flow rate of air is also given, CP is there, delta T is given, condenser capacity is given. So outside means entering temperature and leaving temperature also we can obtain. So we can go for LMTD approach. So first equation, that is LMTD approach. So we write the equation as the fins are provided. So that's why we consider overall heat transfer coefficient is the function of fin surface area. So the total surface area including fin. So that is 80 and LMTD. Now we have to QH dot is given, which is already given, that is 22. UT we need to determine based on the heat transfer coefficients and areas. 80, that is our final answer, that we have to obtain this. And LMTD also we can obtain, but LMTD we again require one more temperature. So in order to calculate that temperature, we use MCP delta T equation. Now here again, m dot is not directly given because it is cubic meter per minute flow rate is given, that is volume flow rate is given. So with the help of volume flow rate, first of all, will density we can assume, that is, if the density is not given, because air is a standard fluid, if the density is not given, we can consider as 1.2 kg per meter cube. So with the help of this expression and volume flow rate, we can calculate the mass flow rate. So mass flow rate of air we have estimated. Then CPA of air, even though it is not given, we can assume at 1.005 kilojoule per kg Kelvin. QH dot is given. These two quantities are given. TI is already known to us. So only unknown is TO. So TO comes around 49.25 degrees Celsius. So now we have all four temperatures. Actually, three temperatures required for condensing and evaporating gases. So condensing temperature known to us, and air entering and leaving temperature known to us. So accordingly, LM, this is 40 degrees Celsius air in, 49.25 degrees Celsius air out, and 55 degrees Celsius condensing temperature. So theta 1 is the difference between condensing temperature and entering temperature. Theta 2 is the difference between condensing temperature and leaving temperature. So LMTD we can obtain. So LMTD we obtain. Now we calculate UT. So this is a fin tube, and there are two resistances we consider. So 1 upon UT80, that is equal to 1 upon HT80 eta T, because this fin efficiency is also given, plus inner side heat transfer coefficient. So as the inner side there is a refrigerant, there is no question of falling. So the same equation on outer side is provided with the fins. So that's why. So now multiply both side by 80. Then we have this expression. Now in this expression, HT is given because air side heat transfer coefficient is given, and HI is also given, refrigerant side heat transfer coefficient. Efficiency is given. So this term is given, HI is given. Now only AT by AO. So instead of AI, AT by AI, we can write AT by AO and AO by AI, because AT by AI is not directly given, but AT by AO is given. So we split this as per the mathematical rule. So AO get cancelled. It remains same as AT by AI. So AT by AO is given because it is given at 20, and AO by AI. So because the diameters are given, generally this heat transfer area is pi dl, but the length is common, so length get cancelled. So instead of AO by AI, we can write DO by DI. So DO is 1.27, DI is 1.12. So by using this, we can calculate UT, heat transfer coefficient. Now you might have realized it is always under the influence of lower or two film coefficient. So this is called as the analysis of the numerical. So heat transfer coefficient inner side is 2600, outer side is 16.4, but the combined overall heat transfer coefficient is even lesser than the outside heat transfer coefficient. It's very low, and that is because of the fins also. If the fins not provided, even this value is less than 16.4. So in this way, we got all the values. So QH known to us, UT we have calculated, LMTD we have calculated. So only unknown is AT. So this is fin surface area, that is around 176 meters. So this is the area of the fin, including the bare tube area. So this is a simple numerical of air-cooled condenser. Some air-cooled condensers only in order to calculate the capacity. So generally, the previous expression in terms of heat rejection factor, altitude correction factor, TD correction factor, maybe these correction factors given in the numerical. So few numericals are in the assignments. You can go through these numericals and you can solve, because only in order to calculate QH, there are different expressions are available, but rest of the processes remain same. It's a heat exchanger analysis. So this is about the air-cooled condenser. As far as water-cooled condenser is concerned, so we'll take the next problem on water-cooled condenser. So here the problem statement is determine the length of the tube in a 3-pass shell and tube R22 condenser. So it's a 3-pass shell and tube with 108 tubes for 40 TR chiller. So here the cooling capacity is given. This is not a condenser capacity, because this is chiller capacity is given, and the chiller is associated with condenser, shell and tube condenser. The condensing temperature is given, that is 43 degrees Celsius. The heat rejection ratio is given. So one heat rejection ratio uh, is given. Heat rejection factor or heat rejection ratio, that is 1.25 is given. Water is cooled to 30 degrees Celsius in the cooling tower. So as the water is cooled in the cooling tower, so definitely this is the inlet temperature of the condenser, because after cooling it goes to condenser. The temperature rise of water may be taken as 4.8. So again, all three temperatures are given. 43 degrees Celsius condensing temperature, water in-out temperatures. Use integral fin copper tubes. Integral fin tubes are used with OD 1.59, ID 1.37, with 748 fins per length of the per meter length of the tube. So in 1 meter length, there are 748 fins. And the fins are 1 meter, 1 mm thick and 1 mm high over tubes. So the integral fin tubes information is given, or tube information, ODID, the fin height, fin thickness, number of fins, all the information is given. So that is to calculate the different areas. So area with fin, bare tube area, inner tube area. So with the help of this information, we can calculate. Determine the length for the plain tube as well length we have to determine. Allow for 10 bottom tubes for subcooling. So 10 tubes, additional tubes are used for the subcooling. This provision is made in the shell and tube condenser. Condensing temperature is given 1180 watt per meter square Kelvin, and water side heat transfer coefficient is given, that is 6432 watt per meter square Kelvin. Now here you can say the condensing coefficient, because this is the configuration of shell and tube. So obviously the condensation is taking place outside the tube, and if water is flowing through tubes. So again, the fins are provided. If you see, the fins are given, but obviously integral copper fins, whether it is inner side or outer side. So actually it should be on outer side. Why? Because outer side heat transfer coefficient is less. So fins are always provided of the lower, for in the side of lower of two film coefficients. Means the film coefficient which is low, on that side generally fins are provided. So now here condensing coefficient is low. So on the condensers, condensing means condensing coefficient means the surface, outside surface. So outside surface the fins are provided. Fouling factor is given. Obviously the fouling factor is on inner side because water is flowing through inner side. So obviously fouling factor is from inner side. Efficiency is given. So this is the problem on shell and tube condenser. We already taken one numerical on shell and tube DX type evaporator. On the similar basis, we will solve. This is slightly only in that particular case, the fin tubes, the tubes are plain. Here the tubes are provided with the fins. Now we have to calculate the length. If the dimensions are asked, definitely the basic equation required, that is Q is equal to UA LMTD. So this is the equation. But first of all, we have to calculate Q. So heat rejection, that is equal to capacity. Capacity is given 40 TR multiplied by heat rejection factor. So heat rejection ratio is given. It comes around 175, 8.83 kilowatt. Then as area is asked and LMTD is given, this is the basic equation we start with. So that is, again, the fins are provided at the outer side. So UT, AT, LMTD. In this case, UT expression, that is 1 upon UT, AT, that is equal to outer side heat resistance, and outer side resistance is provided with the fins also. So fin area, fin efficiency, and heat transfer coefficient. That is condensing heat transfer coefficient, which is given. Plus inner side heat transfer coefficient, which is also given. HI is given, that is water, and AI is also given. Plus fouling factor. So this is a fouling factor case. So 1 upon HI, HF is given, because if you see, it is a reciprocal of it, the unit, from unit we can say the fouling factor is 1 upon HF. F is nothing but 1 upon HF. If you compare the unit of H and unit of fouling factor, it is the inverse of film coefficient. That is fouling film coefficient. If you Now, in this case, we don't know the area. So first of all, area calculation will do with the help of the information given. This is not a plain tubes. The fin tubes are there. So area calculation is slightly complicated. So now we consider 1 meter length of the tube. So suppose this is a tube and the length of the tube is 1 meter. Now you can see here, these are the fins provided. Fin length is given. So this is height is 1 mm. And the thickness here in this case is small, but thickness is also 1 mm. So this is OD and this is DT, and we have to calculate the area of the fin. So fin area we can calculate by using this. So in 1 meter we have considered 1 meter length. So in 1 meter length there are 748 fins. So number of fins multiplied by area of one fin. So area of one fin we can calculate. First we calculate the area of the fin of this portion. This is a surface. So this surface, it is actually pi by 4 dt square divided by or minus pi by 4 do square. So as the both surfaces are available for this side or other back side. So both surfaces, that's why twice. So twice into dt square minus do square by 4. So this is the area available. And also thickness is 1 mm. So the outer surface, so it is pi dl, that is circumference area. So this thickness is t, that is 1 mm, and that is pi dt. So pi dt. So this is for one fin. So number of fins in 1 meter length is around n. Now all these values are given. This is 748. dt we can consider because this is 1 mm. So 1 mm this side, 1 mm this side thickness. So it is 2 mm. OD is 1.59 plus 2t. So dt we get 1.79. Then DO is given 1.59. Thickness is given 1 mm. We convert all the dimensions in meter. And n is 748. So area of the fin we can calculate. This is area of the only fin. But area of the fin plus bare tube area. So bare tube area we can calculate, that is pi DOL. So L is 1 meter. But this total in 1 meter length, I think there are 748 fins. So 748, and each fin has the thickness is 1 mm. So 1 into 10 is to minus 3. So 1 minus 0.748. So this is the area available for bare tube. So that is a space area. So area of the space. So from that we can calculate the base area. So this is a base area because we are talking about this is heat transfer area, not cross sectional area. These are the heat transfer area. Then the total fin area, the total area at the outside, because this 80 we have to calculate. This way 80 is equal to area of the fin plus area of the base tube. So it comes around 0.134. Now outside and inside tube surface areas, so it is pi dl. So AO is pi dol and AI is pi dol. So L is common, so it is L is 1 meter because we are considering 1 meter tube. So AO and AI we have calculated. Now if we take a ratio, because here if we multiply by 80, the ratio is required. So 80 by AO and 80 by AI. So here if we multiply both side by 80, so 80 get cancelled. So 80 by AI is required, that we have obtained, and also 80 by AI. So 80 by AI mostly required here also. So now in this case the only unknown is UT, then we can calculate UT. Now UT known to us, UH dot known to us, already obtained. Now we have to calculate LMTD. In order to calculate LMTD, again the temperatures are given. Condensing temperature 43 degrees Celsius. Water entering the condenser is 30 degrees Celsius. Not directly given because water is cooled at 30 degrees Celsius in cooling tower. So after in cooling tower it is cooled. So the cooled water is again recirculated through the condenser. So water inlet temperature is 30 degrees Celsius. Water outlet temperature is 34.8 degrees Celsius. So inlet and outlet temperatures are given. The condensing temperature is given. Means theta 1, theta 2 we can calculate. Similarly, LMTD we can calculate. So LMTD comes around 10.43. Now in this way we have QH value, we have UT value, or we have LMTD value. So putting these three values here, we can calculate the total heat transfer area. Now don't get confused between this heat transfer area and this heat transfer area. This is for a particular length, only for 1 meter length. This is 1 meter length, and this is the total fin surface area or total outer surface area for the entire, uh, including all tubes. This is 80. We have to calculate AO, but we know AT by AO. So with the help of this ratio, first of all, we calculate AO. So AT by AO, this our AO is nothing but 80 upon 2.684. So we get outer surface area of the uh, uh, tube. Now outer surface area is also given by the expression, that is number of tubes into pi, the surface area of the one tube, because we have to calculate L. Now in order to calculate the number of tubes involved, now it's already mentioned allow 10 bottom tubes for subcooling. So there are total 108 tubes. So out of that, the bottom tubes are spared for the subcooling. It's only the condensation, for condensation purpose, 98 tubes are used. So we have to consider here the tubes available, because area we have calculated using only condensation process. Not subcooling is not considered here. So we have to subtract here 10 tubes from the total tubes. So total tube is 108, because 10 tubes are spared for subcooling. So the number of tubes for condensation, because while calculating this total area or consequently this outside area, we have considered only a condensation process. So 108 minus 10 is 98. So 90 is the number of tubes. Then DO is already given, that is 1.59 centimeter. We convert it into meter. So only unknown in this equation is length. So length comes around 2.06. So this is the length of the condenser, 2 meter. So that is for entire all tubes. That is 98 plus 10. But while calculating, most of the students will make the mistake here. That is by considering the number of tubes, because only we have to consider the number of tubes for condensation process, because it is already mentioned allowed 10 tubes for subcooling. So it takes into account only condensation tubes. So accordingly, we have calculated the length. I think this is the final answer. We have to calculate, determine the length of the tubes in 3 parts. This problem can be extended in the same problem, how to calculate the number of tubes per pass, and also what is the velocity of water through the tubes. Now number of passes are given, because this is 3 pass, so number of passes is given 3. Number of tubes, now in this case we have to consider all tubes, that is 108 tubes are there. So because including 98 plus 10, so all tubes we consider. So number of tubes per pass, that is around 36. So the number of tubes per pass. So that is total number of tubes divided by number of tubes per pass. Now pass means there are number. This is single pass, we can say. This is double pass. Double pass means this is one pass, and again it returns, that is second pass. In 3 pass system, this is one pass, then return pass number 2 pass, and this is third pass. Third pass, so in every pass now, as per there are 36 tubes. So 36 tubes here, 36 tubes for this section, and 36 tubes for remaining section. So we are considering this. Now we have to calculate the velocity of water through the tubes. Now through tubes, water is flowing, obviously configuration, and shell, there is a refrigerant. Now first of all, we have to calculate the mass flow rate. Simultaneously, the mass flow rate flows through 36 tubes. So the formula of mass flow rate is what? That is density of water into cross-sectional area of one tube into velocity. Rho AV is the mass flow rate, and multiply by n dash. N dash is the number of tubes per pass. So At a time, the water flows through 36 tubes. Okay, so this is 36. There are 36 tubes in this particular zone. So 36 n dash is 36. Now from this we have to calculate the velocity, because velocity is generally associated with the mass flow rate. So mass flow rate, that is equal to rho a v n dash. So in order to calculate mass flow rate, again we use the equation of heat transfer, that is balance equation. That is condenser heat is dissipated to the cooling water. So heat rejection in the condenser is equal to the heat absorbed by the cooling water. So because we know the heat rejection that we already calculated in previous numerical, then temperature rise of water is given, means delta T is given. CPW is 4.187. So only unknown is m dot W. That we can calculate. That is 8.74. Now this m dot W known to us, rho W is already known because it is water. If it is, even though it is not given, we can consider it as 1000 kg per meter cube. Now the cross-sectional area, this is obviously this is inner cross-sectional area, because water flowing through the flow area for water is inner cross-sectional area. Inner diameter is given, that is the inner diameter of the pipe is 1.37. So from this we can calculate the cross-sectional area. So we have the value of m dot W, we have the value of rho W, we have the value of cross-sectional area, we already have the value of number of tubes per pass. So only unknown is velocity. So the velocity of water in the tube is 1.644 meter per second. So it is recommended that velocity should not exceed 3 meter per second. So it is also necessary to check the value of velocity of the going fluid. It should not exceed 3 meter per second, because if it exceeds that value, generally the pressure drop is considerable, or that is called as the penalty cost. So penalty cost is greater than the benefit cost, that is enhancement factor. That is because increasing velocity leads to increase the heat transfer coefficient, but the golden mean should be there. So the ratio of that is enhancement factor and penalty factor, it should be greater than 1, because enhancement of heat transfer and penalty factor means it leads to increase the pumping power. So it should be less. So that limit is generally for 3 meter per second. So here it is 3 meter per second. So in one particular problem, we have covered all the parameters. Generally, the problem in actual case problems is not lengthy. Some part is asked, but in order to have covered everything in one particular numerical. So during the practice session, these numerical will be helpful for you. That's it for this particular topic. At the end of this particular topic, you should be able to size air-cooled condenser. Means how to calculate the length, maybe diameter, and for air-cooled condenser as well as shell and tube condenser. Then also you could be able to determine the operating parameters, like in this case the temperatures or velocities. Pressure drop also you can calculate. We are not considering here pressure drop. Pressure drop also, once you get the velocity FLV square by twice GT, we can calculate pressure drop as well. Or predict the performance of existing condensers. If the existing condenser is available and if the design conditions known, what should be its performance, means any unknown temperature we can calculate. So this way we have finished the condenser part, that is types of condensers and numerical of on the condenser. As far as evaporator and condensers are concerned, mainly the weightage is for numerical part, not for theory part, because theory part is only for information or to just revise your the syllabus you already covered in RAC. So next lecture will focus on the next important device, that is expansion valve. Again, we'll discuss the different types of expansion valve, and at the same time we'll discuss the thermostatic expansion valve, the characteristics of thermostatic expansion valve, installation practices of the thermostatic expansion valve. That is the most critical component in all expansion valve. Setting of thermostatic expansion valve is little bit difficult. So that part we are going to discuss in the next section. Thank you very much.